Welcome to real-world examples on optimizing .NET performance. I'm Stefán Jökull Sigurðarson. I'm Icelandic. I'm a principal software engineer at Lucinity in Reykjavik. Also Microsoft MVP and have a been Pwn contributor, maintainer. And that's a link to my blog if you want to check it out. I'm going to go over a few topics here today. A lot of them have to do with memory allocations and the garbage collector in .NET. Value versus reference types, that's like heap, stack memory techniques, for example, for memory pooling, stack allocations, boxing, serialization, NDNS, channels, which I wish more people knew about, and then some benchmarking and profiling tools. Let's see if we can get over all of this. So, starting at the beginning with memory allocations. .NET is a managed runtime, as you know. What that means is that when you start up a .NET process, it allocates a contiguous heap of memory for each process, and it manages it for you. As in, it takes care of allocating and cleaning up the memory that you use. And this process is maintained by the garbage collector in .NET. Now, there's a link there to the fundamentals of garbage collection. And to optimize the performance, the garbage collector splits the heap into 3 generations, called 0, 1, and 2. And that's to help it manage like different lifetimes of objects that you're allocating. It also has a separate heap for large objects. There's objects that are bigger than 85,000 bytes, which is called the large object heap. We'll get to that in a bit. So the garbage collector basically consists of 3 phases. And this is what it runs for every generation that it collects. It marks the objects that are still alive in that generation, relocates them if it has to, and then it compacts that heap for that generation. And this is done to make space for all the objects that you might be allocating. Now the generations are, like I said, 0, 1, and 2. Generation 0 is where all your new objects get allocated when you create them. Reference types, that is. And if generation 0 is full, the garbage collector has to run a collection on that generation, releasing objects so it can make space for the new objects that you're allocating. And objects that survive get promoted up to Gen 1. That's sort of how it keeps track of like short-lived objects and long-lived objects. Compacts that generation. Gen 1, very similar. If there's not enough memory that gets freed up in generation 0, it does the same thing that it did in generation 0 to Gen 1. Survivors get promoted to Gen 2, which is the final one, and that's pretty much where all long-lived objects end up in the end. And similar to generation 0, if there still isn't enough space, it's going to run a Gen 2 collection. Gen 2 collection is a bit different, so objects there are usually just objects that live for long. That is, they've survived for 2 collections, at least generation 0 and 1. And collecting a generation, as you see, means that it has been doing all the generations before it as well. So a generation 2 collection is called a full garbage collection. And by definition, it's the most expensive one. That's also the only collection that actually collects things from the large object heap. But the large object heap, due to like those mostly being like big objects, is not compacted. So generation 2 is expensive. To run quickly over like reference versus value types, reference types are the types that you normally new up or are objects. Examples of those are strings, objects, classes, and arrays. But value types do not get allocated in heap memory, so they don't get cleaned up because they don't have to. Those are int, bytes, characters, for example, bools, and structs, like instead of classes. Now, the difference between those, for example, when you're calling methods, is reference types get copied by reference. So you can think, like when you're sending a reference type as a parameter to a method, the value of it is not copied. You're just sending a pointer to that reference type. Value types, however, get copied. So like if you create a string, send it to a method, and that method changes the string, it's going to change the original object. However, if you send an integer into a method, and you, for example, increment it, the original integer is not going to get modified because it was copied before it was sent to the method. So knowing all this, then we can pretty much at least get a good sense of how we can increase performance. Like, best thing, of course, is to not allocate at all, because then the garbage collector doesn't have to do anything, but that's unrealistic. We're always going to have to allocate something. So a good aim for us to do is to try to keep the objects that we have short-lived, and to keep them small to avoid them ending up on a large object heap, because, as I said, that only gets cleaned up as part of a Gen 2 collection. And to sort of show you a little bit of an example of this, if we want to convert a string to UTF-8 bytes, this is something that a lot of us have probably done at some point in time. However, this is where an allocation takes place, because we need to put that string, create a byte array for it, and convert it into that byte array. But we can actually avoid this allocation through some tricks, and that's where we get to memory pooling. There's a class called the array pool. It's good because it actually keeps a bucket of arrays for different types. That's why it's a generic. And you can rent arrays from it and then work with it. And once you're done working with it, you can return it again. Now, there's a gotcha here. You have to remember to return it, because if you finish up all the arrays in the pool and you haven't returned them, it's going to have to start creating new ones. But it's not going to clean the other ones up because they're being referenced by the pool. So if you don't return them, you're going to end up with a memory leak. And a good way to do that is to use a try and finally. I'm actually not doing that in this example, just to keep it short. But this is how it works, for example. You rent bytes from the array pool, and you can actually use that array, for example, to turn a string into UTF encoded bytes. And then that get bytes call is not going to allocate any memory, because it's already been allocated as part of the pool, so you can reuse it again and again. There is a helper you can use, which is called the memory pool. It's very similar to the array pool, actually uses an array pool underneath, but it helps you take care of the renting and returning by implementing an iDisposable. So you can just use a using declaration for the memory that you rent, and it'll get returned eventually when you're done using it. Another one of those things that you can do is stack allocations. Now, they're a bit different because they are not allocating objects on the heap, so they're not creating objects that need to be cleaned up. So by definition, they are often a lot more performant and a lot faster to do, but there are caveats to it. There are limitations. You don't have an endless amount of stack space. I think we've all seen what happens, for example, if you have an infinite recursion, you end up with a stack overflow exception because you run out of stack memory. That's why you cannot do this or use an endless amount of it. There are other limitations as well. You cannot use it in async methods, because the compiler will generate all sorts of state machines and method jumps between it, so there's no way for it to keep track of the stack allocated memory. And you have a limited memory space. You should never assume that you have more than just a few kilobytes of memory to use. Also, when you're stack allocating memory, it is best to allocate a constant size, because that allows the compiler to do a lot of optimizations to make the allocations faster. There is one hint in there which I didn't put on the slide. You should never use a stack allocation in a loop, for obvious reasons, because you will, of course, eventually end up with a stack overflow exception if you do that. Now, there is a trick you can use to combine stack allocations and the array pool, where you can pretty much at runtime decide which one you're going to do. So in this case, we decide, okay, we're going to allocate or have a limit of like 1 kilobyte. We create a nullable reference to a byte array, which is the pooled array, which will only get populated if we need to go to the array pool and can't use the stack allocation. Then we figure out how many bytes we're going to need. If it's under the stack allocation limit, we use the stack allocation. Otherwise, we use the array pool. And then at the end, we check if we actually rented an array and return it if we have to. Now, to put this into perspective and sort of show you what happens, like with the UTF-8 example, if we run a benchmark on this for like 3 different sizes, a string that has 64 bytes, or 64 characters, 512 characters, and 1024 characters. For short strings, you will actually see that just like directly allocating it just using the plain method, is actually faster than using a memory pool. And the reason for that is because the memory pool, like I said, uses idisposable. So there's overhead involved there. It has to have a try finally around the idisposable. It has to call the dispose method. So for short strings, memory pool is actually more expensive there. But as the strings get larger, you can see that the standard method gets slower in every case. And in all of these cases, stack allocations are the fastest ones. If you look at the column there that says allocated, you can see how much memory is being allocated in each case. But you can see, for example, when I have a string of length 64, I'm allocating 88 bytes of memory. There are extra 24 bytes there that are being allocated every time. And I'll get to it later why that is. You also see that those same 24 bytes are allocated in the memory pool instance. And that brings us to boxing. When you have a value type that you need to convert, or not convert, you need to store it as maybe it implements an interface, the runtime can't store it directly. It has to put it inside an object class and store it somewhere. So even if you have a value type, if you treat it as an interface, you're going to be allocating memory because it needs to be put into that object. So, for example, this happens when you wrap a value in an object class. For example, let's say you have a list of like iComparables. If you put an integer into that list, you're going to allocate memory because it's going to need to treat that value type as an interface, and interfaces are actually objects. So memory needs to be allocated on the heap every time you need to box a value type. The memory allocated on 32-bit machines is always, well, at least 16 bytes. It depends on the size of the value type being boxed. And it's at least 24 bytes on 64-bit machine. That's the 24 bytes that I was showing you earlier. Because we had our memory pool used as an idisposable, so it needed to wrap it in an interface. That's why that method actually allocated 24 bytes, even though we were using pooled memory. And this is the reason. For example, if we put an integer and box it, this is the object that actually gets created in the memory layout. You get an object header that depends on if you have a 32-bit or 64-bit machine, how big it is. It needs a method table pointer, then it needs the actual value. And because it needs to like align everything, it needs to align the objects to like specific architectures, it needs to have 8 bytes for padding as well. So, an example here of boxing. Let's say I create an interface. I want to create a serialization interface. And to minimize allocations, I create a struct to implement that interface. So all that interface does is it takes a span of bytes and then it's supposed to write that object into that span. I then have a method called serialize, which takes any object or struct or whatever it is that implements the interface and serializes it to the bytes in there. But again, to minimize allocations, I created a struct. I'm using stack allocated bytes for the destination, so there are no allocations there. And I call the serialize method. But because we're treating it as an interface, this is going to allocate memory regardless. This is always going to allocate, at least on my machine, which is 64 bits, at least 24 bytes of memory. But there is actually a sneaky way that we can get around this. We can use generics to trick the compiler to say, my serialize method is going to be generic this time, but I'm going to restrict it to taking objects that implement this interface. So when I actually now call this method, the compiler is going to basically create an implementation of this method using the struct directly instead of the interface, so no boxing will take place. But there's two other things that actually happen here as well. In the previous version where we were actually using the interface, it also needs to do what's called a virtual method call. Because it's receiving an interface, it doesn't know what the object is that's coming in, so it can't do any optimizations. Well, it technically can if you have very few types implementing the interface, but usually you should consider that it doesn't. And that brings us to something called inlining. If we have a small method that doesn't do a lot, then the compiler will sometimes, instead of making your code call that method, simply take the content of the method and put it instead of the method call. So it saves a method call, and the code version, the generated code version of the method becomes a little bit bigger, but it's faster because there's no overhead in having to copy parameters and everything else. So this actually gives us 3 benefits. We get rid of the boxing, we get rid of the virtual call on the interface, and we actually allow the compiler to start inlining things. And for example, in this case, the implementation of my serialize to bytes method was just taking an integer, converted to bytes, because an integer is just 4 bytes in memory. The difference in performance here is actually quite dramatic. If we use the interface call, pretty much every call takes 6 nanoseconds. But using the generic interface, it goes down to 0.4. It's actually 93% faster than the other one. Now, just to be clear, this is a micro-optimization. You might have a lot of code that you would change to do this, and you wouldn't notice anything in your application. But if your application is doing a lot of things with either interfaces or struct types, you should see a difference. And speaking of serialization, that brings us to NDNS. NDNS is something that is dependent on the architecture of the machine that you're running. Machines can be like big endian or little endian. And then when it comes to networking, a lot of libraries or protocols say that you should be sending things in network byte order. Network byte order is just big endian. And to show you what I mean by NDNS, if I take an unsigned integer with this value, which converts to the hex AA, BB, CC, DD, on a big endian machine, this is stored in that order in memory. It's going to be stored as AA, BB, CC, DD. But on a little endian machine, which is probably most of your machines, it's actually stored in memory as DD, CC, BB, AA. So if you would send this integer over a network that's expecting this to be in the correct order, you would actually be reversing the integer without knowing it. So this is something you need to be aware of, for example, if you're writing cross-platform serialization code or sending stuff over the network according to different protocols. So there are, of course, ways that we can just get around this. We can detect the NDNS or just reverse the bytes if we want to. And this is what RabbitMQ.NET Client used to do. This is not very pretty code. If you've used bitwise operations like ANDing, ORing, or shifting things, you might realize what it's doing. It's basically taking the bytes in that long and it's reversing them. But it's trying to do it all without allocating anything. So there are no temporary variables that are really being used that require allocation. But of course, for us to be able to do this, we need to read it as an unsigned integer, so we're sure that all the bytes are in the correct place. However, there is an easier way to do this, because .NET has a thing called binary primitives, which does the same thing. We can read 8 bytes. We can simply say, read this as a big endian. There are also write int64 big endian and write operations for most other value types that you have. And to visualize this, if you look at the actual assembly code that gets generated for these 2 methods, it looks like this. And I'm going to highlight the important part. The old method is on the left. Those are all of the CPU instructions that needed to be run just to make sure that we were returning the bytes for lit long in the correct order. Using the binary primitives class, it boils down to 1 instruction, because it turns out our CPUs actually have a single instruction that just does this. Take this memory thing, reverse it, and store it somewhere else. And again, like with the other benchmark that we saw, the difference is actually quite dramatic. The new method is actually 95% faster, and I think we can all agree on which one is more readable as well. So that brings me to something called channels. This is one of the things that I wish more people knew about. If you've ever written, for example, a concurrent application that uses multiple threads and you need to pass things back and forth, you might have used a lot of like different constructs, like queues. You might have used like locks around them to make sure that like one thing is pulling stuff from the queue, one thing is putting stuff in there. This is what channels do for you. It's made to sort of do this producer-consumer pattern. It has optimizations for different scenarios, like do I have multiple writers, do I have a single writer, single reader, multiple readers, whatever. And it has both async and synchronous interfaces as well, because as soon as you start doing something like this async, you have to do a lot of complex things. For example, you might have used a queue and a lock, you might have used a concurrent queue and semaphores, and then you start running into like task completion sources if you want to have this async and whatnot. Channels just make this easy because they take care of all this for you. Out of the box, channel comes with two implementations. There's an unbounded one, which just basically says I can put as many items in the channel as I want, which is good, like if you want to do things quickly, but you have to be really sure that you can actually process things faster than they come in, because otherwise they're going to run out of memory eventually. But for those cases, you actually have the bounded channel. The bounded channel can set a maximum number of items that can stay in the channel, so it's great for buffering things up. You can say, like, I want to create a channel that takes like 100 items, and if it's full, the producer is going to have to wait until the reader is actually taking stuff out of it before it can put new stuff in. If we look at just a simplified example of this, let's say we create a method at the top that processes an integer, and just to simulate some work, we're going to randomly sleep for up to 100 milliseconds, asynchronously, of course. Then we write to the console if this number is odd or even. Then we create another method, an asynchronous method, which processes the channel, and you can see that it takes channel reader as a parameter. It can asynchronously for each through it, so for every item that comes in asynchronously, it's going to call the process method. If there are no items to read, this method is not going to block and take up one of our threads. It's just going to yield it back, and it can go do something else. Then we create a bounded channel, 10 items, and we start the consumer process. Now at that point, it's not going to do anything because there's nothing in the channel. Then we just do a simple for loop, put 1,000 items in the channel, asynchronously, of course, because we have to wait for the reader to take them out, because we can just keep a maximum of 10 items in there at a time. And we write when we've actually written something to it, and once we're done writing, we complete the channel. And we have to complete the channel to let the reader know that there are no more items going to be coming through, otherwise the reader would just run forever. But this is to signal to it and say, hey, like, you're done. And then we wait for the consumer to finish. And if we just run this really quickly, this is what it does. Just runs very easily. This is just two asynchronous tasks. One is writing, the other is reading, telling you if it's an odd or even number. But we, of course, have multi-core machines, so we might want to do this in parallel, take advantage of them. When we're using channels, we can actually just focus on that part of the code. We don't have to worry about, like, do I have multiple readers or multiple writers? Channels just take care of that for us. So all we got to do, really, is change the processing method, or the one that actually reads from the channel. And this is what I actually like in this example, because doing this in parallel is actually simpler than not doing it. Because we have asynchronous parallel helpers for this. And to give you an idea of the difference, we can do something like this. I think this is even still running. Doing it in parallel becomes something like this. And it's done. Taking full advantage of the cores that we have on our machine without really having to focus anything on how we were producing or consuming things, just focusing on the actual thing reading from the channel. So, I've gone over a few things that we can actually use in these cases. Now, this talk is about how these things were actually applied in the real world. And I actually applied these things on the RabbitMQ.NET client. RabbitMQ, for those that don't know, is like it's a queue, message queue, and it uses the AMQP protocol. Just to give you a very quick overview of what it does. Connections have channels. Like, these are not the same channels I was just showing you. This is the RabbitMQ term channel for multiplexing purposes, so you can be using the connection for multiple things at a time. And channels issue commands like create a queue, declare a queue, delete it, or publish a message, whatever. Commands eventually, when they get sent to the server, are serialized into frames. Frames are just byte arrays, really. They consist of a header, payload, and an end marker. To show you sort of like a very simple explanation of the layout, a frame looks like this: 1 byte for the type, 2 bytes for the channel. Payload length is 4 bytes. Payload, different depending on what is actually being sent. If I'm creating a queue, I need to send the queue name and other things. If I'm publishing a message, I might be sending headers, etc. And then there's an end marker telling you that like this is the end of the frame. The payload layout is like what would actually be put into the frame payload. 2 bytes for the class ID. Class ID can be like queue or exchange, whatever, and then the method ID, which is like create, delete, publish, things like that. And then the arguments that go with it, like the queue name, for example. So we can see that we have things we need to serialize, things we need to deserialize and work with. So what the RabbitMQ client did before we actually made these changes, when it was sending a command, this is what it did. Step 1 was it created a memory stream. It wrapped that memory stream in a network binary writer, which was basically a helper class that did all the serialization, like big endian serialization and other things. Wrote the commands to the network binary writer, which put it on the memory stream. Grabbed the resulting byte array out of the memory stream, because now we have serialized this into bytes. Sent that to the actual network stream. Needed to lock it, of course, because we can't be having many people trying to write bytes to the network at a time. Wrote it and had to release the lock. Now, there are multiple problems here related to what we were just going over. Always creating a memory stream is expensive because it's allocating a new byte array under the memory stream at all times. Now, you can tell the memory stream to use an existing byte array if you have one. And you can tell it to, like, you can initialize it to a certain size also if you want, but in the cases where we're having commands, we have no idea how big or small it's going to be. The memory stream, depending on how big the command is, might have to resize the array, and that means allocate a new array, copy everything over, making more space. And it might have to do this multiple times if the command was really big, for example, if you're publishing a large message. Another problem was that the helper class, the network binary writer, always assumed it was running on a little endian architecture. So usually a pretty safe assumption to make, but if it was to be run on other architectures, this would fail. There's a lot of custom serialization logic, which I show you, for example, with the big method that was doing all the like bit shifting, ANDing, ORing, whatnot. Doing a lot of these things is not good for the CPU because like you're basically like creating a very big assembly code out of it. Doesn't inline very well because it gets complex, which is not good for the compiler either. And doing all the locking, of course, on the connection slows things down as well. Like if you were doing a lot of things in parallel, you would be getting into a lot of lock contentions. Saying like, nope, you have to wait till I get the lock so I can like write this frame because if someone else is writing another frame or a big frame. So every frame means like had to take a lock, write it, release it, so it added up quickly in case you had like high concurrency. Every frame implementation that had like knew how to serialize it was a class. And like I showed you earlier, classes are reference types. So that means even if we were just creating a simple command that was creating a queue, we needed to start allocating bytes, or extra bytes at least. So we needed to figure out a way to solve the problem. So we thought, okay, instead of writing commands to a memory stream, let's just implement a frame interface, knows how to calculate its size, so we can actually know beforehand how many bytes we're going to need. And then the interface like tells it or instructs us on that it needs to know how to write itself to those bytes. We changed the serialization, deserialization to use the binary primitives, as I showed you before. So like it was properly cross-platform. Code was a lot easier to read as well. And then we decided to use the channels as a buffer between the connection and the outgoing frames. So instead of always taking a lock on the network connection and start writing, we would just put it on a channel. So after the changes, what we did, like how we would actually send commands to the RabbitMQ server is we would calculate the command size, because we have an interface to do that. We rent an array that is big enough for us to write into it. We, again, have an interface, so we know how to write to that array. Send the array to the channel writer. And there is just a single reader picking everything up from the channel, writing it to the network stream, and once it's done, it sends the array back to the array pool. So in this case, we're hoping we at least not allocate anything. To validate that these changes were actually doing what they were supposed to be doing, we needed to profile and benchmark the changes. So created a simple RabbitMQ test application. What it did was it opened the connection to the server, created a channel and a subscriber, sends 50,000 messages, gets them back. We decided to have like a big payload. Wait until it receives them all back and then quits. So doing the math on this, we were sending less than 2 gigabytes of data over the network, or should be. Now, before we actually made all these changes, this is what the RabbitMQ client did. It allocated 7.14 gigabytes of memory to send 50,000 messages. So to send less than 2 gigabytes of messages, we were allocating more than 7 gigabytes. Those are not like allocations that were all being done at the same time. So like the client didn't take 7 gigabytes of memory. Like it was constantly like allocating it and cleaning it up. But you can see that like it's allocating a bunch of bytes, it's allocating a bunch of memory streams, and it's actually allocating or creating, and the garbage collection having to collect like 4 million objects. So this is not very optimal. After we did the changes that I just showed you, it went down to this. 99 megabytes in total allocated to send this, because we can simply reuse all our byte arrays again and again and again. Also reduced the number of objects allocated from like over 4 million down to 1.8. And this was actually just by making these changes that I actually did in there. There was room for a lot of improvement more, and it has actually been improved. I think we're actually down to like using this same benchmark. I think currently we're around 30 or 40 megabytes that get allocated. So this is sort of a way that you can actually apply things like this in the real world with actual real world benefits. But doing this is, as with everything else, you can't just like go all out and start optimizing everything without actually knowing what you're supposed to be optimizing. And so we're going to need some tools to do that. And to go over some of them, if you're using Visual Studio, it has actually a built-in profiling tool, which is really, really nice. And it has actually been improved a lot lately. It's become a lot faster than it used to be. And it's built into, like I said, built into Visual Studio. But if you're not using Visual Studio, JetBrains has memory allocation tools as well that you can do memory profiling on. You can see, for example, it shows you like visually how much memory is in each generation, like the generation 0, generation 1, 2, or the large object heap for that matter, and it shows you like the difference in what happens when it actually does collections. It also has a really, really nice snapshotting feature, so you can take snapshots as your application is running and actually compare them. So you can see like the difference in, for example, how many strings I've been allocating between the snapshots, or how many of them are getting cleaned up, or how many of them are still left. So you can use that, for example, to track memory leaks. Another tool JetBrains has is .trace. This is a CPU profiler. So instead of profiling your memory usage, you can use this to like profile your application and see where it's actually spending all its CPU time. You can also use it to see if you have a multi-threaded application. You can see all the context switches going on, see which tasks are running, or which threads are actually doing anything. It can also help you spot, for example, if you have threads that are blocking or waiting for something when they should be like yielding their tasks to other threads. So it's very good to look at thread utilization as well. I forgot to mention, for example, the Visual Studio tools. They actually have both a CPU and a memory profiler built in. So that's pretty handy. If you want to really get down to something nitty-gritty, you can use Purview. It does not have the best user interface, but if you get used to it, like I would not recommend that you start using this tool like to begin with. Use something simpler to begin with. But this tool is really, really powerful. It can show you a lot of things if you know what you're looking for, and it can do profiling, memory allocations. And it can even start looking at things like when you're jumping from managed code into native code. It can tell you, for example, like if you have a managed application that's opening and opening a lot of files, it can actually show you once it goes upward to the operating system to open a file, and it can show you like, Defender is pulling in there, trying to like scan the file before I'm opening it and everything else. So it's really, really good. But it takes some time getting used to. Benchmarks. The benchmarks I show you, or like the results I showed you, were created with benchmark.net. Benchmark.net is really easy to use, and it's really powerful. It's great for these micro benchmarks. It's not very good at showing you, for example, like it's not very good at benchmarking an entire application that does a lot of things. It's best for benchmarking like small pieces of code. And it gives you results in like multiple formats. You can get a text format, markdown format. It can give you reports, for example, of, as we saw, the memory allocations. It can even give you reports of the assembly code that gets generated. So you can start running this, seeing the difference in code generation, and a lot of other very, very cool things. You can also, for example, like it's done here, you can say, I have a benchmark, I want you to run it on these different types of the .NET framework and compare the results. So you can see the performance improvements, for example, between .NET Framework versions, or .NET Core versions for that matter. Another tool that I'm really fond of is sharplab.io. This is pretty much a website. You just go there, you paste in some C# code, and they will actually compile it, and it can show you the results. It can show you, for example, if you have a C# code where you're using a lot of the new syntax, it can show you the actual C# code that it gets turned into. It can also show you the intermediate language code, the IL code, or even the assembly code that gets generated. So this is really nice as well. It's easy, for example, if you want to share code generation with someone else, you can just like copy paste URLs, and it will actually, the code is actually usually a part of the URL in there. Also has, like in this case, you can see that probably in the middle there, there's an x64. You can like see how the different code is generated depending on what architecture you're picking. So that's a really nice thing. And another thing that I'm really fond of is PowerUp. It's a tool made by Bartosz Adamczewski. I think I'm pronouncing that correctly. But it is a tool he actually created because he likes looking at compilers, seeing like the different things compilers do, or different compilers, different things they should be doing and aren't doing. And this works not just for .NET code. This can actually show you code generation for, I think, Golang, Rust as well. So I'd highly recommend that you take a look at this tool if you wanna see what actually happens. So I think that's pretty much it. I decided to leave some room for questions if you have any. This is a lot to go over, to digest, so please bring them on if you have any. Can't see anything. Any questions you have? Right?
About channels.
Yep.
Is there a way to use channels together with React's NX library?
Sorry, is the question if you can use channels with the RX library?
Yeah.
I,
Translation like
Not that I know of, but I would guess that it would not be very hard to do. It might actually be a good fit in some cases. It might be helpful. Anyone else? You're gonna have to speak up because I can't see if you're raising your hands. All right. So, thank you very much. That's my blog.